Hi everyone, I'm Guangyao. I'm currently a fourth-year PhD student in University of Maryland. In this video, I will present our recent work on communication-aware multi-robot coordination with submodular maximization. This is a joint work with Ishat, Lifeng, and my advisor Pratap. In this work, we are mainly concerned about multi-robot coordination problems. It turns out that many multi-robot coordination problems can be formulated as submodular optimization problems, which is a special type of discrete optimization problem. In a multi-robot system, communication is very important when we want to optimize the submodular objectives to choose actions for robots. In the centralized case, we need to transmit all the information to the central decision maker. In the distributed case, robots need to exchange information with his neighbors. One observation we have in this paper is that actions that maximize the submodular objectives may disconnect the team. Take this active target tracking, for example. The goal is to maximize the number of targets observed at each planning epoch. To achieve that, we want robots to be separate from each other as far as possible to reduce the overlap in sensor footprint. But being too far away from each other may break the connectivity of the team. Therefore, the key problem we consider in this paper is how to jointly optimize the connectivity and the submodular task objective function. This work is related to three lines of work. The first line of work is on submodular maximization within a network. In this work, the topology of a network is usually fixed, and they don't consider the influence of actions of robots on the network topology. They are concerned how certain graph properties limit the performance of the classical greedy algorithm. The second line of related work is on connectivity maintenance using algebraic graph theory. There are many papers on this topic. Research on this topic is usually on optimizing the second eigenvalues of the Laplacian matrix, and they usually treat the control task and the connectivity task separately. Our work is different from this work in that we need to jointly consider a discrete optimization problem as well as the connectivity maintenance. This paper is also related to the research on submodular maximization over the general graphs. Papers on this topic are usually about how to choose different nodes within a graph. But their result cannot be applied to our case because of the mobility constraints. In our case, each robot can only go to positions within the reachable set of that robot. The formal statement of our problem considered in this paper is that at the current planning epoch, robots' positions induce a connected graph. We want them to form another connected graph when they move to the new positions in the next planning epoch, meanwhile maximizing a submodular objective function. Several things should be noted here. The first one is that there may be several time steps for each planning epoch. And also, during the transition between the two planning epochs, robots may be disconnected from each other. So in this sense, the connectivity we considered in this paper is equivalent to intermittent connectivity. Moreover, in this paper, we assume a disk communication model for the robot. The main contribution of this paper is that we propose this new problem called communication-aware submodular maximization problem, and correspondingly, we also propose a two-stage heuristic algorithm to solve this problem. If we view this problem from another perspective, we can have some insight into this problem. Suppose that we can generate a set of candidate trajectories for each robot, and each candidate trajectory will correspond to one vertex within the reachable set of that robot. In this figure, for each robot, it has 4 candidate trajectories that corresponds to 4 destinations. If we think this way, the problem is equivalent to how to choose one vertex for each robot to maximize a submodular objective function, meanwhile forming a connected graph. One naive algorithm to solve the proposed problem is the sequential greedy algorithm. It works as follows. The one robot will choose one action first, and then one of the neighbors of that robot choose another action. That neighbor robot must connect to the previous robots, and also that the neighbor robot should have the largest marginal gain. Such a process will guarantee the connectivity by construction. However, the solution can be arbitrarily bad. In this example, if robot 1 chooses one action first, it will go to the local information-rich area. It will go downward, and then it will force other robots, robot 2 to robot 6, also go downward. So the robot 2 and robot 6 will deviate from the global information-rich area. As a result, the solution can be arbitrarily bad. By contrast, in this paper, we propose a 2-stage optimization algorithm to solve this problem. There are 2 stages. The first stage is on graph topology generation. In this stage, we generate a desired topology for the next planning epoch. And in the second stage, we solve optimization problems to move robots to realize the desired topology and satisfy the constraints. In the first stage, there are 3 steps. The first step is we let robots to do the greedy selection without considering the communication constraints. And using the greedy selection in the second step, we will construct a weighted graph. The cost of that graph is defined as this. The intuition here is that if the distance between 2 robots is less than the communication radius, then the cost is 0. If the distance is greater than the communication radius, then the cost is proportional to the distance. In the third step, we will run the minimum spanning tree algorithm to find a connected graph to use that as the desired graph topology for the next stage. In the deviation minimization stage, we consider the problem as follows. Given the current positions x1 to xn of the robots, and we also know the greedy selection x1j to xnj for robots, we want to find the new position x1 star to xn star for the robot, such that the weighted sum of the deviation is minimized. Here, the parameter wi reflects the readiness of robot I to deviate from the greedy selection xij. If wi is very large, it means the robot is less willing to deviate from xij. The first constraint here corresponds to the graph topology constraints, and here the graph gt is generated from the first stage, and the second constraint corresponds to the reachable set constraint, and the last one corresponds to the safety constraint. Such a problem can be handled by the available commercial solver like Groovy, and in the application we use the Groovy to solve the problem. We validate our algorithm in this active target tracking example. The objective here is to observe as many as possible targets for each planning epoch. We assume a simple motion model for the targets, and we use Kalman filter to estimate the position of all the targets, and we assume a simple reachable set for all the robots. We assume it is a circle, and we uniformly discretize that reachable set. we run the target tracking for 20 epochs and computed the average number of targets observed. The baseline algorithm here is the sequential greedy algorithm, and we also use the greedy algorithm as an upper bound. Here, the greedy algorithm means that the average number of targets observed in each planning epoch without considering the connectivity constraint. It serves as the upper bound of the algorithm performance. The simulation suggests that our algorithm in general can observe more targets than the baseline algorithm and very close to the upper bound performance. Also, as you can see from this video, during the task process, the team is connected all the time, and despite that, the topology will change. In sum, in this paper, we propose a new problem called communication-aware submodular maximization problem. And correspondingly, we give a two-stage approximation algorithm to solve the proposed problem. In the future, we plan to extend this work from two directions. The first one is that we know that deviation minimization process will actually destroy the submodular structure. So the problem is, can we still give some performance guarantee in such a case? Yeah, this is one important direction we will consider. And another direction will be, can we just use one-stage approximation algorithm instead of two-stage algorithm? Because in such problems, the graph topology and the action selection are inherently coupled. So it would be great if we can just solve the problem using one-stage approximation. Thank you for your attention.